IAFSM webinars that we like to host. We usually put on, just a few a year, maybe four or five. And we like to cover different topics, different manufacturers, different software. And so today I'm pleased to say that we have both Ananda Fowler and Nguyen from Riegl. And this was prompted actually from our conference last year in Orlando, and Ananda gave a very good presentation, lots of good information on the technology. Unfortunately, he was a little rushed, so we wanted to make this up to him because he had a lot of good stuff to offer. So just a note about the IAFSM. We are having another conference in San Diego this year, and that's going to be in November. And if you go to our website, iafsm.org, in fact, what I'm going to do is just type it in to the chat window here. You'll see that on the page, on the front page, there's some information that will lead you to the conference registration and such. So without further ado, I'm going to hand it over to Ananda to get started. And also, if you have any questions, just drop it into the chat window. I'm going to be monitoring these. At the moment, everybody is muted, but I think we'll work the questions just through the chat window, and depending on the timing and such, I may or may not jump in. Otherwise, I will just wait until the end. Okay, Ananda, if you're there, see if we can hear you, and I guess we can get started.
All right, thanks, Eugene. All right, can you hear me okay?
I can hear you fine. Hopefully everybody else can too.
Okay, perfect. So thanks for taking some time out of your day or evening, whichever the case may be, to sit in on our webinar. We're going to talk a little bit about Riegl technology, and I will go a little deeper in depth about just what we do and how we do it. So I'll start with a little bit about our company, talk about some of just the basics of LiDAR, so that we all start on the same platform. I'll go into waveform, which tends to be a big scary subject for people, but hopefully I can take some of the demystified fear out of it. The byproducts of waveform, which are the attributes which are associated with each point, we'll discuss. So Tan will give you some practical applications for these attributes, and then it will come back to me. I'll give you some software updates on Resolve, and then we'll go back to Tan again, and he'll give you guys a bit of an overview of how Riegl stands in the world with regards to forensics. Then we'll take some questions at the end. Okay, so a bit about Riegl. These are two visionaries. In principle, our company is more a scientific organization than it is business endeavor. Of course, we do make money. It is for profit. But if you talk to either of these individuals, you will always find the primary focus is on creating something new, innovating, bringing the world to the next level in laser technology. We now have more than 170 people here in Horn, Austria. You can see the little chart. We've grown over the years, and we continue to grow. So although our focus is incredibly scientific, the benefit of being super innovative is that there's always a demand for your products. So just to give you a bit of a history, not everyone knows our company. So I'd like to start basically over 40 years ago with some of the groundbreaking patents for time-of-flight LiDAR. So these are patents created by Dr. Riegl. Then moving forward in time, so he started a company, Riegl Laser Measurement Systems. He produced one of the very first single-point lasers. And then in the early 80s, he produced a 2D profiler, which of course most people don't know that existed. Upgraded this to really an enterprise version, which was then used not only in tunnels for doing profiling, but also on rails. Actually, you can see one mounted on the front of a rail system, which counts as one of the first mobile scanners. In the late 80s, made some automation tools for cars. So of course now we're really familiar with autonomous navigating cars. But this process was started with some German manufacturers in the late 80s. A bit too soon, as you can tell. So things are just now taking off that way. Made a laser tape, really small handheld device, the smallest in the world at the time. In the mid-90s, we released our first airborne system. 1997, we produced our first 3D laser scanner for the European Space Agency. In 1998, we commercialized the technology to make our first Z-series laser scanner. In 2000, we launched a Space Agency initiative, so there are Riegls in space now. In 2003, we combined photogrammetry with the LiDAR system for terrestrial scanning, the first in the world to do this commercially. 2004, we introduced waveform technology. Of course, I'll discuss this a bit more later on. This is very groundbreaking for our industry. 2008-9, we took waveform to the next level by doing real-time waveform processing, which we refer to as online waveform. 2009-10, we came out with the mobile system, updated in 2011, introduced the VZ4000 in 2011 as well. 2012, we came up with the Topo Hydro airborne system, also came out the VZ6000, and these innovations continue and continue and continue. So dual channel airborne system, Q1560, which is a really high altitude system. There's basically no competitor for this system on the market today. That's also the year we introduced Resolve. It's been 2 years now. So a lot of what I'm going to talk about should theoretically be old news by now because it's software and it's 2 years old. So, and of course, last year we introduced the VUX UAV system. And this year at our user conference, we introduced 2 new models of UAV systems. So now we actually have 3 UAV systems. Our headquarters is in Horn, Austria, where 170 people work. We have an administration building, which you see here. We have research, development, production, and then we also have a CNC shop next to it. So our company spans a really broad number of applications and industries. So we're primarily going to be speaking about terrestrial today, although we'll touch on unmanned a little bit because there's a lot of synergy between them. But we also make airborne systems all the way up to high altitude systems going up 20,000 feet. Mobile systems for rail, marine, transportation corridors, etc. Unmanned, exactly, and industrial, which isn't necessarily, if you're in the industrial region, then you'll know of our systems. That's kind of where we started. We still manufacture a good number of systems for that. On the terrestrial side, we have the VZ6000, which is really long range. So it reaches distances well beyond 6 kilometers. It's non-eye safe, pretty much only going to be used by scientists. It takes a lot of care to make sure that everyone's wearing special safety glasses, etc. We have the VZ4000, which is eye safe completely in all modes of operation, reaches distances beyond 4 kilometers at very high pulse rates, which is an innovation, novel innovation in itself. Last year we introduced the VZ2000, which for all intents and purposes operates, behaves, looks just like a VZ400 or 1000, but it's 3 times faster. It's operating at 1 megahertz. Of course, we have the VZ400 and 1000. These have been the basis of our terrestrial offerings for a number of years now, and they're still incredibly competitive, which is amazing. So, getting into time-of-flight laser scanning. Just going to start with some basics. So the speed of light is 300,000 kilometers per second, or about 30 centimeters per nanosecond. When you're scanning, typically you're going to talk in nanoseconds or picoseconds. The properties of light, so there's basically 2 light's a duality, which is really cool. It's an electromagnetic wave, but it also has some real physical properties like photons. It has mass, which is incredible. So it's actually 2 different things in one flow, which is incredible. So I'm going to give you a basic background on the 2 different types and how they're used in scanning. But before I jump in, I want to make sure that first we dispel any, intimidation by the word waveform. So waveform just simply refers to a graph of amplitude over time. So you could use this for sound. This is used for a lot of industries. But if you've ever seen an equalizer, like in a car or a stereo MP3 player, that was waveform. So waveform is not, an incredibly crazy new technology. It's really a term that has a broad application anytime you have electromagnetic radiation and you monitor it. So in this case, I'm showing you an equalizer, and then of course you have some sound waves, which we all know and familiar with, and at the bottom you have the amplitude of those sound waves in principle. So that's really well defined. The only real difference between the sound wave and what we're calling waveform in principle is that we're digitizing it. So you take original sound wave, which is analog, and then of course you digitize it, it becomes digital. Here's some more examples. There's different ways to visualize this process because of course it's by light or by sound, and we can't actually see the waves by our eyes, so we have to visualize it some way. And at Riegl, we typically show it as you see in the upper right box. So just a bar graph showing amplitude values. So in principle, you shouldn't be intimidated by the term waveform. It's something you've seen probably multiple times per week already. We're just using it to refer to light and a specific way of digitizing light. So before I jump into waveform, let's talk about the different technologies. So there's two primary technologies used in laser scanning today. One is phase-based scanning. So in principle, for phase-based, you were using the phase of the light itself, so the wave of the light. So this light is transmitted, and I'm just summarizing this really briefly, so I'm bringing this slide up here, just this image, so you know it's actually a much deeper science than I'm about to make it sound, so I don't want to insult the phase-based manufacturers, because it is a very complex science indeed, and I'm just going to make it really simple for everybody. So in principle, I'm going to talk about the line in the middle, which is sine wave modulation. But really, you have the carrier signal, you're mixing the sine wave modulation, you get a phase modulated signal you see below. But that's a little too deep for our discussion today, so I'll skip past that. I just want to let everybody know it's not quite this easy, even though I make it sound like it. So you transmit the wave, and it comes back, of course, and you somehow get a distance out of this. How does that work? Well, there's a physical relationship of the light to a distance on the real world. So the light has a physical property. The wavelength is a certain length. This is the phase length. So we can drag that down here. And then we're also measuring when the wave comes back to the laser, exactly what the incidence angle is when it's received. And again, this is a gross summarization, but please don't shoot me. So in principle, you can think of it as you measure the angle, you're measuring the distance. They're basically tied together. It's way more complex than this, I assure you. But that's the basic concept. Angle equals distance, or phase incidence angle equals distance. And that's how phase works. You can use time for some different attributes, but in principle, that's how it breaks down. Now, to make sure that you accurately record or correct distance, typically you use a very long phase. So that it goes out and comes back and you're still in. We'll talk about pulse technology today. And pulse technology, which everyone knows, is time of flight. So laser goes out, comes back, how long did it take? Okay, multiplied by the speed of light, that's your distance. That's the basics. But the cool stuff is, light's actually made of a bunch of little things called photons, right? And these have mass, they're physical reality. So a wave is, but it's somehow mystical electromagnetic stuff. But photons have real impact. If they hit things, it's basically how your skin can burn and stuff like this. So when we transmit it from the laser, we record the amplitude of that energy as it goes out. That's this little pulse bump you see down here. So as it's transmitted, we get a real-time recording of that. And it's on a fixed scale. This is really important. So when we digitize this, it's all on a fixed scale. And that means all of it's related and relevant. So that beam flies out, smashes into some object, in this case a wall, and the photons are scattered everywhere. This scattering means that the energy that comes back to the laser will get less and less and less the farther away you are from that surface. So in the end, the closer you are, the more light comes back, the more amplitude, the further, the less, just because of the way the light hits that surface. So even though when we fire the laser, it's very tight, when it hits, it scatters everywhere. So the photons go everywhere, and you can see on the bottom here we have blue, which represents a timeline. So some of those photons come back, they impact the laser, the receiver, and we convert that into an electronic signal, and that's how we have some echo amplitude you see down below, the little bump. Now, the time of flight format's really simple. Range equals total time of flight, t, divided by 2, right? So that's just how far it went out. We don't care about how it's come back, the time, all that, but times the speed of light, and that's your distance. Very straightforward. But we take this a bit further, and we compare the returned echo with the pulsed echo. And since we digitized it, since we're digitizing all this in real time, we're just storing it digitally, just like a wave file for sound, then we can analyze this. You can think of it kind of like the difference between having a record and an MP3 player or a wave player or a FLAC player. The record, of course, you put a needle into vinyl, and as sounds are transmitted in, it wiggles and creates a vibrating spiral line. But you can't really compare that record with another one. It's a record. You can just play it. That's all you can do. And that's really the difference between analog and digital. Analog is just as valid as digital, but digital you can analyze. So that's what we'll get into in a second. So these waveforms, in principle, are just amplitude over time. So usually there's exactly this Gaussian curve. It has a geeky formula on the right side, but I won't go into it. In principle, I just want everybody to know the amplitude is just simply peak energy. So it's 2D measurement at that point in time, and that's what we call amplitude. And amplitude, of course, changes over distance. So this is a graph of amplitude over range. Of course, in the near range, it's kind of counterintuitive. You would think, okay, well, the farther away the reference surface gets, the less the amplitude gets. Yeah, it makes sense, except there's some geometric properties of the scanner that change those dynamics at closer range. So I'm not going to go into that. It goes into calibration and things we don't need to talk about at the moment. So, but eventually you hit what's your commonly accepted formula, which is a logarithm. No, it's actually a 1 over, I believe it's s to the 4th power for amplitude being returned from the surface over range. So it's the same reflectance surface over distance. And of course, you simply receive less light from the same surface as that surface gets farther away. Now the difference here is we've calibrated our systems so we know exactly how much energy we've transmitted and exactly how much energy we've received. And the difference between those tells us a lot about that surface. So if we take that little bit and then we scale it for that distance, we arrive at reflectance, which is basically a calibrated amplitude that's scaled for distance. And this reflectance value is constant. So I've taken away the scale because they're on 2 different scales, but in principle, it's the same by dB. So this is a decibel scale on the vertical axis, and I haven't put any values because it doesn't matter. In principle, I just want you to show amplitude really varies with distance, and this is the same surface shown in reflectance. That's the blue line. So reflectance is very constant on the same surface, no matter the distance. And this is only up to 50 meters here, but we've measured out to, as far as I know, like 500 meters a kilometer. We get basically within 1 dB for reflectance all the time. Okay, so a practical look at that. So this is a view of a street scanned by a VZ400 by amplitude, and you can see exactly what we discussed. At close range, the building's very bright, it's red. At long range, way back there, it's blue. And if you look at the cobblestone down below, it's very high, a lot of energy coming back right below us. And then as we go away, as the street runs away from the laser beam, then you can see less and less energy comes back. But if you calibrate for that, then you receive reflectance. And there you can see the cobblestones are actually really regular, no matter how far away they are. So they have a certain spectral property, and we're picking that up with our calibrated system. And the buildings, you can see the same thing. I'll go back again. So really dark, and it goes to blue, and then it's a lot more normalized. So this is what reflectance, the visual difference between reflectance and amplitude are. And Tan will tell you in a little bit how that's useful. So going back to waveform, of course, we pulse the laser. We receive the energy immediately off of the glass of the instrument. This is called the system response. That echo is bounced off of the building and comes back. That's very straightforward. But what happens in a multi-target environment, like if you scan through a tree? You pulse, the laser goes through the tree, hits the wall, and comes back. And of course, people will always say, yeah, but how are you getting multiple returns in the tree? Like, it's a laser beam, it can only hit one thing and come back. But if you think about it like a flashlight, if you shine a flashlight into a tree at night, you see all the branches inside the light beam. You see, pretty much everything visible that's illuminated by the light. That's all light flying out, bouncing off of all those branches and coming back. So although our laser beam is quite small, it actually does encounter multiple objects quite often. And because we're digitizing all this information, we can analyze it just a split second later on the instrument, which lets us do some cool stuff. So let me walk you through the digitization process. At the top, you have an analog signal. So we have the pulse, the tree, which is multiple branches and stuff all mixed together. You can see that multiple peaks. And then the building, very clean signal on the other side. We digitize that in real time with an analog digital converter. And then you get these samples over time that I was describing earlier. And then, of course, we turn that into hard disk information. So that's what you have with all the zeros and ones, just a visual representation of hard drive data or solid state or whatsoever. Then from that information, we extract the amplitude, which is the next line down. I don't know if you can see my mouse, but probably should have put a rig around it. And then we extract deviation. So, and I'll now discuss what deviation is. So you've seen reflectance and amplitude from waveform data. So it's basically digital amplitude and digital reflectance. Now let's look at waveforms in a bit more detail. So that's the digitized information, zeros and ones. Then you can, if you want to post-process, you take only the digitized information of amplitude over time, and you would do Gaussian fitting normally. And this is quite precise, but it's very computationally expensive and hard to do in real time. So it's important to note while we're here, the peak of these waveforms represents the point. So the peak is the most critical part. That's the critical mass of the light, and that's where the thing is that you're measuring really is. Sorry for the title, that's actually not correct. So we transmit a pulse, and this is what one pulse might look like. And then we get an echo like that, and we try to fit that echo back to the original pulse. So this is the difference between post-process waveform and real-time waveform. We know exactly what the pulse looked like, so when the return comes back, we try to fit the two together. So this is what the fit looks like. It's a best fit, and this is called, basically we're comparing the echo signal to the system response, and we do deconvolution, and the result is some minor difference, which is this guy. So that's the difference between just the shape of the light which we pulsed out and the light which we received. Just this shape difference, not the amplitude or the size, because we fit those, is what we're going to store. So that's called pulse shape deviation, just that guy. And just a quick example, a little more scientific example. Deviation is good for this. So we've taken this tripod with what's known as a Fowler star, and then we turn the Fowler star sideways, and then when we scan it, as with all scanners, because the pulse, the laser beam itself is longer than the distance of the object, which you see here in green, and then the wall, which is in green, then they're mixed up. The 2 points get basically mixed up, they get convoluted. But in the mixing, because we're doing waveform analysis, we see the peaks and we see, the waveform is a bit stretched out. There's a bit more deviation to these. And we store all those values so that we can filter it. So without doing any fancy anything, we just simply run a deviation filter. And down here at the bottom, you can see a deviation value of 50. 0 means it's a perfect return, but Tan will talk about that in a second. So 50 is there. Then 25, you can see more of the false returns are filtered out. And then 6, there's no false returns. And this is only possible with waveform analysis. And this is done in real time on the systems, on our VZ scanners. Because I was asked to go into really a bit more technical depth, I will. So it's not quite as simple as just a 2D waveform. In principle, every scanner is unique. It has unique physical properties, unique electrical properties, and we have to calibrate for that. So we have basically a library of waveforms which cover quite a spatial domain depending on how the scanner is used and what it's doing. We calibrate all these applications in principle, so all the dynamics of the system response, and we model that in 3D. And this is really what we're fitting over time. So it's a bit more complex. I won't go farther than that just for the sake of time. Here's an example of a view of waveforms inside Brascan Pro or Resolve. You have a scan position on the left side, and then there are multiple returns. So actually this is calculated 6 returns. You can see the graph of the returns on the top here. And if I zoom in on one of the returns, so here's 1, 2, 3, 4, 5, and 6 returns. If I zoom in on 4 and 5, you can actually see the waveform of those points. So you can see 2 peaks here, and a traditional analog system wouldn't be able to extract 2 peaks. You'd probably get 1, and it would be the combination of both of these convoluted, which means it wouldn't be very accurate. Or you'd get the first one, but definitely not the second one. But with waveform processing, you get both. So to summarize, just to recap, of course, LiDAR comes from radar. It was used to be called laser radar. Similar concept. There was generally 2 types. Of course, there's much more than that. There's like 6 or 7 kinds of laser scanners now, but these are the 2 main for surveying. There's the phase-based and the time-of-flight. Riegl only produces time-of-flight. And inside of time-of-flight, there's analog on the left and digital on the right. And we used to make analog systems, but now we pretty much only make digital systems. If it has a V in front of the scanner name, then it's digital. And there's 2 types of digital systems. There's the kind for offline analysis, which is the mostly airborne systems. And then there's real-time digital systems, which is on the right, so real-time or online waveform processing, and that's the Riegl VZ scanners. The end result is very precise, very accurate, and attribute-rich point cloud. To give you a physical example, this is the Colosseum, of course, in Rome. It was scanned a couple years ago by one of the guys at the company. He just ran a room real quick, no plan, no whatever, just one scan, so he did. But taking the data, so here's one look at the data. This is 27 scan positions combined. This is amplitude, and again, that's digital amplitude. It's not analog. From that digital amplitude, we extract distance, and we of course are measuring theta and phi. That's what you see on the bottom there, theta phi range. It's the two angles in the distance. So you have a 3D point cloud. This is by height, so we have a 3D attribute. Then we have the deviation attribute. Again, Tan will show you how this is useful in the real world in a minute. That's shown here. Of course, if you have a camera, then you have RGB or true color as well. If you calibrate for the amplitude, then you receive digital reflectance or calibrated reflectance. And then finally, because it's a waveform processing system, you have multiple returns. And here we're showing yellow first returns, blue last returns. And you can see mostly it's edges where you see first returns unless you get vegetation, or in the case where you see what appear to be yellow windows, that's actually mesh net. So we're mapping the mesh net, but of course getting what's on the other side as well. So all in all, just one scan from Riegl system gives you basically 6 dynamic attributes, 6 types of information. So I'll hand this over to Tan now, and he'll give you some practical insight on how this is useful and how you can use it.
All right, thanks, Ananda. Hopefully you gave me the controls.
Oh, so sorry, give me a second. Yep, now you have them.
Great, thanks. So I want to go over the practical application of the point attributes. So everything that Ananda had described earlier, I want to show you what it looks like and how can you apply it through the data sets itself. Okay. I'm going to talk about deviation, scanning worst scenarios, rain, snow, dust clouds, and whatnot. Everything that you would experience out in the real world. And I'm going to show you a little bit about reflectance versus RGB. A passive versus an active system, right? So I'm going to display some road marks, skid marks, and passive straight signs, and how it pops out when you look at a scene in RGB versus, a scene in reflectance versus RGB. And there's value in both, of course. And then I'm going to show you what the multiple returns capability looks like. So earlier, Ananda was talking about online waveform processing, multiple return system. I will show you how the system can be used out in the real world to penetrate vegetation and then still receive objects in the background. So deviation, Ananda explained earlier, deviation is the property of driving the changes of received echoes pulse shape compared to the emitted pulse shape. You will see this in target surfaces that are textured and our orientation with respect to the incoming laser pulse, right? So you would see deviation pulse shape, especially in through vegetation, will increase the pulse shape and thus will increase the deviation value. Also, tilted surfaces where the surface normal vector is not parallel to the laser beam will broaden the pulse and thereby increase deviation value. So the deviation 0 is the ideal case and means no distortion. The receiver pulse fits 100% to the emitted pulse, right? But when you're out in the real world, there are objects behind objects everywhere. So 9 out of 10 times, you're going to receive some type of deviation within the point cloud. And there are ways to eliminate and filter out this deviation to achieve the high certainty of the particular laser point. So here, sorry, that was a little bit too fast. So here we have an image of pretty much scanning the worst scenario, right? So the worst thing we encounter out there, and we do encounter it everywhere, whether it's here in the U.S. or over there in Europe, there's going to be rain, and it's inevitable. You're going to see it. Well, it doesn't eliminate the practice of scanning the rain. It will just gives you more points than what you want. So here we have a scene to where we have the scanner set up, and it's raining. Not only the objects behind the rain, it's picked up. Also, the rain is also picked up. But by using a deviation filter and also a reflectance filter, which we used here, we're able to select just the points that are the rain. So everything that you see in this scene that's selected in red in principle should be just the rain, right? And once we select those points, we can then delete them, hide them, or assign the points to different attributes. And then therefore eliminating the rain and still capture the scene that we intended to be there for. So, and this also works on dust and also in clouds, fog, snow, and whatnot. Recently, I'll just quickly explain. I did a presentation on penetrating through fog and visibility range, and we had some great results. So perhaps maybe one day I'll get to share this presentation with you on penetrating through fog. So let's talk a little about reflectance and RGB, right? So our reflectance is a calibrated reflectance reading, right? So it's non-range dependent, meaning that if the scanner is placed at this particular position, when it shoots at a surface, it will have the same reading as the scanner will move forward or backward or away from that particular object. It will still have the same reading, which is a very useful tool when identifying skid marks, blood splat, gun residues and whatnot. We'll see that in a minute. And also, it's a user-defined scaling. So the color that you'll see throughout the next couple slides, it's all user-defined. It's not particular to red, green, or white. It could be to a grayscale or to a color scale, right? And another attribute that all of us are going to see is RGB. So all of our scanners are equipped with Nikon D800. And as the technology improves, we will also use better cameras to put on top of our scanners. And these particular cameras are really good. I mean, in my opinion, they're professional grade cameras, so you'll get very good results from these cameras. And it also has HDR imaging capability too as well. And of course, we use a 20mm lens, so it's considered to be a near-range photogrammetry system. So let's take a look at some attributes with color versus reflectance. Yeah. So here we have a wall that we scan, and as you can see, focus your eyes on this shed right here. So what you're seeing is true color. It's just actually a point cloud, which is very, very good. I thought it was a photograph at first, but it's actually a point cloud. So this is true color. This is what the naked eye will see, and this is what the camera sees. So this is what you see. But when we switch the view over to reflectance, as you can see, now we can actually see graffiti behind the wall. Again, this is an active system. It provides its own laser source, and the calibration and the reflectance is calibrated to the intensity of the return of each laser pulse. Yeah. So the reason why you can see the graffiti behind the wall is because when whoever painted this wall, without painting the entire wall black, they just left the graffiti alone. The attributes of each return from the area that has the graffiti, it's either stronger or weaker from the rest of the wall that does not have graffiti. I hope that makes sense. So therefore, you can see the letters on the graffiti wall. Right. Again, this is an active system, so it provides its own light source. And whenever the light hits a surface that doesn't have the graffiti, it reflects differently versus when it hits the surface that does have the graffiti. So therefore, you can see the graffiti pop up when viewed in reflectance versus true color. Right? So that's a very strong and powerful and unique tool that our system offers. So let's take a look at some more. So here we have a top view of a mock-up scene that was done at our office. Yeah, right. So we can see structure, we can see the cars, we can see the tape, the cones, the lines, the striping, and whatnot. And it looks great. We can identify the object very easily, right? But let's go ahead and change it into reflectance to see what we see. Right? There we go. So not only we can see all the objects, the people standing around, the trees, the curbs, and the lines, we also see other attributes. Like, for example, if you look at the lower left corner, towards the lower left corner, you can see all the skid marks, or you can see the width of the skid marks. And objects just, it begins to pop, right? So that's, and you can see your cracks in the asphalt are more identifiable. So if you look at your, I don't know if you can see my mouse, but if you look at this area right here, I'm going to go back into true color. You can't really identify the cracks that well. Of course, if we were to zoom in and whatnot, yeah, we can see it. But from the same position, I simply changed it to reflectance, which is a calibrated reflectance too, by the way. You can then start to see the cracks in the asphalt and whatnot. So if there was a stain that was not identified to the naked eye or to the RGB camera, I'm very confident that reflectance can also pick it up. Okay. All right, so now let's look at some skid marks. So this is a different mock-up scene that was set up by the Florida Highway Patrol. So whatever you can see here is what you see. It was what the camera saw, right? So the camera provides on an external light. For example, our goal here is to identify skid marks. Yeah? So once we flip it into reflectance, we can then see the skid marks right here, clearly identifiable. We can measure the width and other objects in the scene that we did not see in the true color, we can now see in the reflectance as well. Again, here you can see my scaling is rather from like a more red tone, and then a couple of slides earlier, my scale was from a more blue tone. It's because it's all user defined, and that's the uniqueness of our reflectance. It's non-range dependent, and it's also user defined. Okay, so we'll just quickly talk over the online waveform processing. So Ananda had already done an excellent job explaining this. So I have a scanner here in this particular illustration. You can see the scanner set up at approximately X distance. The object is the roof, but there's a tree involved. So not only it's able to capture the tree, but it's also able to capture the object in the back. So at the last graph at the bottom here, you can see targets return 4, 3, 2, and 1. And now I'll show you how this particular technology can be applied in the real application. So here, this graph shows, or this picture shows the scanner, and I try to position this as accurate as possible to where my colleague had positioned the scanner and tried to shoot this particular scene. This is Amplitude, and you can see there are low vegetation, and to the right there are high vegetation. And in principle, our eyes cannot detect objects behind those vegetation, but nevertheless, light can still shine through it, right? So that's good enough. And here is the same scene, but instead of displaying it in Amplitude, I display the point cloud in the echoes, right? So the echo has accordingly to its return attribute. So the next slide will give you that. So same scene. I just rotated the point cloud a little bit and did a little speedy capture. So pay attention to the echoes over here in the top right. So green represents single returns, yellow represents first return, and aqua, other, and blue is last. So the blue one is what I want you guys to look at. So the blue one is all the blue here that you see on the council and also on the ground was once squirrel who is covered by the vegetation from where we were particularly standing. But nevertheless, with the online waveform technology that we will provide in all of our terrestrial scanners, we can then penetrate vegetation and still achieve the objects in the background. So what can you use this for? Well, I can see that if we're out scanning a scene in a wooded area, whether it's light wood or medium wood or even, I would say, up to heavy density woods area, we can then still detect objects in the back. So there was, I don't know, a body that was 40 yards away from the actual scene itself that somebody had dragged over there, hidden in a bush somewhere. Well, we can then penetrate these dense area or medium dense or low dense area and still get the targets in the back, right? So very, very useful tool. Whether you like it or don't want it, it's there, and every time you scan, you're going to get it. So. And I'm going to talk a little about the software, and then I'll go a little bit more deep into it. Just time is a constraint here for us. So here's a plot view that you can easily generate from our software RiseSolve. It's a scale. You can scale it any way you want. This one's scaled to 1 to 100. You can take measurements from here too as well, from Adobe Reader, I believe. And this scene is particularly captured in calibrated reflectance. You can see each color, and it's, again, it's scalable. It's represented by the surface attributes, right? So dark surface, for example, would be more blue, and lighter, highly more reflective surface would be towards red. That's what I had it scaled. Of course, you can scale it to where you want. So here I'm going to show you a terrain filter that our software has. It's very, very great tool, and I think some of you guys out there has already been using it, so good, right? So here's a scene that I showed you a little bit ago. I just quickly isolated the area of interest. and then I selected the vehicles, right? So it's a sloppy select. You don't have to be very detailed or do fine selecting. You just literally fence out an area of interest, and you use the terrain filter, and then you just hit. Sorry, I'll go back. You just select your settings. You know, I have vegetation, I have vehicles, I have objects, I have noise. I pick vehicle, and I hit the OK key, and the result is my ground is unselected, and my vehicle is only selected. Again, I don't have to delete the points, and I will not delete the points. What I'm going to do is I want to make a carbon copy of the vehicle to hide and to put in another location so I can use it later, right? So the vehicle is then removed, a carbon copy has already been made, and those are the two vehicles only without the road. I can then separate the vehicles and then move it around to my liking and use the data, use the carbon copy data to reconstruct the scene. In the next couple of slides, I'll have to thank Eugene first and after Dave Foster for providing me with this material. So what can you do with the data, right? So here's a scene captured by Dave Foster, and then I believe the data was handed over to Eugene, and the next couple of slides was made by Eugene, so I'll thank him for that too as well. So then you can take the vehicle, rearrange it yourself, and you can get something like that as a result. Very nice, by the way. Thanks, guys. Okay. And I'll quickly go over the workflow. So RiSolve itself is designed and dedicated for the forensic industry, and you can use it for other applications too as well. But we made it especially easy for them, right? Because we want them to get in, get out, produce a point cloud, and then reconstruct the scene, right? We want that. So first you take a scan, right? So this particular scan position takes approximately 3 minutes. Now with the VZ2000, you know, you can cut down more than a third of that. So more than three times fast. Scans at one megahertz is unheard of in my opinion. It's super fast. And then the next part is just importing the scan, right? You take the data, put it into the RiSolve software, and you click register, and then you colorize it, and then you plot it, and then there's an export button, and that's it. You want to simplify it, and you want to make it easy for everybody to use. All right, and then Ananda will take over with the software.
All right, thanks, Dan, for the look inside the practical applications of our technology. So, I'll give you a brief update on RiSolve. RiSolve is really closely tied to the hardware. So I'll just give you a quick overview. So here's a stitch panorama image. I've cropped it just so it fits on the slide, but that's one of the products that come out of the scanner. So you click one button, you get a high resolution scan. Automatically, you get 5 or more words. It's user definable. You can parameterize this. High resolution images, that's what we're stitched to make this view of the Colosseum. And then at the same time, while scanning, the system is recording GNSS data, inclination data, and compass data. So in the end, you end up with a coarsely registered point cloud. We take this information, when you drop it into RiSolve, this is sped up by the way, so this is not real time. It takes between 15 and 45 seconds supposition for what you're watching here, but this is the process. So RiSolve will then, as bad as it is with GNSS, you can see these scans are really poorly placed, 10 meters off, 50 feet off, and it will register them and adjust them. So at the end, it will do a final georeferencing adjustment as well. So everything is very accurate and precise. It's not just stitched together and then maybe it's level, maybe it's not level. It's all level data. So that's basically the key points of RiSolve. So it's easy to import, easy to register, it's easy to filter as well, and it's easy to create a plot or export the data. And exporting has become exponentially easier as well. We've introduced 2 new tools in the latest version. One is the registration power tool. The other is the multi-select tool. With the multi-select tool, you can select multiple of a single file type with a specific naming scheme, and you can export them all simultaneously now. You can colorize them all simultaneously now. You can delete them, filter them. You can run one function on multiple objects with the multi-select tool. With the registration power tool, you can register multiple scan positions using one of these 7 methods. And inside these is actually built almost every conceivable way to register scan data. So just one example of direct georeferencing. You have a few options. You can set the scanner positions. You can not set any position at all if you want. So just modify inclination or azimuth with compass. or you can apply GNSS coordinates that were stored during scanning, or you can apply an external coordinate through the global coordinate system tie point. You can apply a height offset if you like as well. So you run through, you get a report at the end that tells you if the positions were successful, if not. Here's an example. This is the traditional backsighting workflow. This is how it used to be in the older versions. So I have a click counter at the bottom, kind of got a Riegl strike through, sorry. But we click counter. So I'm just going to walk through exactly the process as it used to be. You can watch the click counter go. So this is what it used to take to register one scan position with the backsighting registration method in RiseScan Pro, Resolve, Remining, etc. So it's 19 clicks for one position. Now, you simply select scans, or you can select as many scan positions as you like. You select your registration method, in this case it's backside. Make sure your parameters are as you want them. Hit OK and you're done. That's it. 4 clicks, all your scans are registered. Now again, in Resolve, it's automatic. So you don't even need to use this, but if you need to do some special projects and you want to use targets, or you have something that's out of the ordinary, like if you have to go indoors or you don't have all the sensors available, then you're going to want to augment it with some targets, and that's what this is for. So here's an example. This is registering by free station. In the beginning, it will be real time. So right now, it's all real time. Selected 47 scan positions, set my parameters, say OK, and it registers 1, 2, 3. So it's about 1 second per position that's being registered. I've sped it up now, so this is still about 1 second per position. It works through 47 scan positions, and in principle, it's like automatic registration. Nothing's happening right now for the user. They're watching. So this is about 1 minute, roughly 30 seconds to a minute. And, okay, it's 44, sorry. 44 scan positions are registered indoors using targets. So it's not fully automatic, but it's semi-automatic. So it just gives you some more flexibility. That's what the registration power tool is about. So to give you an idea of this in real time, so I'm going to pull up Resolve and run backsighting registration on those Colosseum scans. So I select the scans I want, or I can use the multi-select tool to select multiple scan positions. Sorry. What's happening? There you go. All right, maybe not. There you go. So I can select all the positions or none of the positions whatsoever, or I just click scans. I'll choose backsighting. Say OK. Use the tie points, skip registered. Okay, now this is real time. You're watching scans be registered in real time. So there's no extra sauce needed here. As long as you use a well-defined workflow, in this case backsighting, so you have a known position from GNSS and you have some reference target for each position, the registration happens that fast. Some of the results from this, I'll jump to that. So this is a large area, and what backsighting allows you to do is really spread the scans out. So some of these scans are 500 meters apart. There's 2 coupled, so that there's a real precise alignment between them. But then between pairs, you can go quite a distance. I mean, this valley is about 500 to 600 meters wide. If you're in the States, it's about a quarter of a mile, maybe a third of a mile apart between these sets of scan positions. So this is just one of the results, and this is done automatically in Resolve. So there's 2 functions. One is fully automatic, and this is done fully automatically if you've done the proper due diligence in the field while you collect the data. The other is fully automatic for small scenes. That's how Resolve always used to work in the past. Wow, that's awesome. It's like old school TV. So we've updated the performance. It's 64-bit now, which means in principle 32-bit limits you to 4 gigs of RAM. Now we have unlimited RAM in principle, and that means larger files, faster processing, more files processed simultaneously, etc. We now have georeferencing support since version 2.0. It's backwards compatible with other definitions of GSM software. It's really easy to import well-defined coordinate systems. So we're accessing an online EPSG database. So you select a well-defined coordinate system that's known by the geospatial community. You can import it. You don't have to know all the parameters yourself. You can apply it. As well, in the new version, we've updated ReamTA TLS to 2.0. It's now 3.5 times faster than the other version. If you're using a VZ2000, you need this. So in principle, what happens is, if you pulse one laser shot and it goes out, and before it comes back, you pulse another one, you end up with 2 pulses in the air. You can end up with up to like 4 pulses in the air with the VZ4000. Like literally, the time of flight is not fast enough, or speed of light is not fast enough for us anymore. So we're actually pulsing light faster than it takes for it to go out and come back. There's multiple pulses in the air on a terrestrial system. So the software calculates all of these points, puts them in the right spot, and then they're seamlessly blended into the overall point cloud. And this process is fully automatic. There's no parameters. You don't have to do anything. So that's new. It's much faster. Some new interface updates. The user interface is now ready for ultra-high def displays 4K. We've gone from something like this, what looks like basically an 8-bit interface, to a modern interface, so it's all scalable vector graphics. Icons are now resizable, so if you want to change your 3D icons or window icons, you can suit you. We're lining up our software products, so now they share more and more a common look and feel. We've set it up so you have fast access to most tools. You'd have to use the software to experience that. We've changed the default navigation mode, so now it's Z is always up. You can't really flip yourself upside down very easily. And it's easy to turn between perspective and ortho mode. It's a click of a button. There's a few clicks before. Doing ortho snaps is really simple. It used to, if you clicked the ortho snap tool, it would send you into space. Now it actually snaps relative to your distance to the object that you're looking at, to a top view, side view, whatever you like. Yeah, there's less icons. It's more well organized to suit the user, so it's what you use most. And of course, we have the new power.
Hey, can you hear me? I'm disconnected somehow.
Hey guys, it just came back. Ananda, I lost you when it said something about the new tool, I think.
Are you there? Okay. We lost Ananda. I can finish it off. I think we're almost done anyways.
Okay.
Okay. So these are some new power tools that we have embedded into the software, and that's it. Power tools as far as viewing, selecting, especially registration. Oh man, he's gonna have to give the controls to me though, otherwise I won't be able to change slides. Let me see if I can try to do it. No, I can't. Yeah, Nana, you still there? Yeah, I don't have control over his.
Yeah, I hear you. Yeah, he may have been just cut off here. Let me see if I can get control here. No, I can't get control of his thing from here, I don't think.
1 minute.
Tan, if I can interrupt, it's Kathy. While we're trying to work on that, I had a question come in while you were presenting. Maybe you can address it while we're working on this. The question is, can you use an iStar to color VZ400 data?
An iStar?
Yes.
Is that a type of camera?
Yeah, that's it's a panoramic camera from NC Tech. It's a little cube-looking camera, and it captures a panoramic image. So I guess the question would be, can you incorporate panoramic images or other images into if you were using a different system, to the software.
Yeah, absolutely. You absolutely can. We've had success integrating thermal cameras, and also, if you guys have heard of it, the Ladybug camera, which captures panorama images. So yeah, to answer your question, absolutely, we can definitely integrate it, trigger the camera, and also colorize the data from the imagery.
I'll tell you what, since we're waiting, if anybody has any other questions, you may want to just type them in and we'll go from there. Hey, Tan, one about the terrain filter. So Is that something that you're setting based on the reflectance or the intensity, or is it the one you showed looked like it was just based on some kind of a height? So you select part of the ground with the objects in it, and then does it just it tries to create a plane or something like that?
Yeah, so the terrain filter, you saw me selecting an area that has the ground and the vehicle, yeah? So what the software does is that it uses an algorithm to detect the first set of points that are on the ground, which is considered a plane. It doesn't create a plane, but it considers the first set of points on the ground as a plane. Then everything else above the ground is considered noise. Now, noise could be anything. It could be a car, a person, a gun laying on the ground, so that can also be noise. So that's as simple as that. And it's all automated, it's completely automated, so you don't have to do anything. And the tools are all preset. All the terrain filter, all the settings are all preset from when we release the software.
Okay, and let's say, for example, other filters. So I was chatting with Dave Foster once, and he mentioned that, let's say, for example, you know how you were showing the top-down view, and you had, you could see like the tire marks or the cracks and things like that?
About how these are used, please.
Oh, hey, Ananda, you there?
Yeah, can you hear me?
Yeah, actually, we had a problem, Ananda. You got cut off when you were talking about the new power tool, so you just popped back in, and Tan's been talking on your behalf since then. So
Okay, great. Okay, good. Then I will leave it be. Perfect time. Go ahead, Dan.
now, do you want to switch over to Tan?
You want to finish your part, Anand? I mean, were you done? Because I didn't have controls of the slides.
Okay, so sorry. I haven't heard anything you've said, so I'll just trust that it's awesome. Go ahead.
Okay. So should we just continue with the presentation, Eugene?
Yeah, I think if there's something that you want to cover very quickly where Ananda left off to here, then you can do that quickly, and then otherwise you can just continue.
Yeah, no, we'll just continue. So Ananda, okay. All right, so Ananda has touched base on some of the tools that were originally developed within RiseSolve, but that is just some of the tools, right? So this whole entire list right here, only the highlighted, all the tools in the box has been touched on. So you can see there are at least another dozen other tools, power tools that we haven't discussed, which we don't have time for. But nevertheless, we have shown great improvement, great development within our software to cater to our existing customers and new customers. Now we're going to move on, and myself, I'm going to finish it up by showing where are we at in the world, right, as far as the forensic industry. And hopefully I get to finish and finish with a video if we have time. So where are we at in the world? So we have the Australia Queensland Police Department, which has one VZ400. Great Britain, which has been a stepping stone for our forensic industry as far as acquiring at least 35 systems in the last few years, and also in the process of acquiring more systems. We have systems in Hungary, which has a one VZ400. The Netherlands, the National Forensic Service Center has VZ1000, and the Swiss guys, wow, these guys are advanced, right? So they started off with two VZ400, and then they later on, we'll give you a quick background. So they have been flying unmanned system photogrammetry for the longest time, but recently they needed a better solution. They needed a more safer solution per se. So what they did was that they bought a VP1, which is our VUX1. It's a small pod scanner that they put on top of their helicopters, right? So now they have airborne scanning capability. And why not do this? Because they already have a helicopter that has to be deployed on every single high-profile mission. So why not just put a scanner on there and do large area scanning? Well, that's what they did. They bought a VP1, which is an aerial scanner. They hooked it up to their their helicopter. Anytime they have a big scene, a high-profile scene that they needs to launch the helicopter for any reason, well, all they have to do is just click start, and they're acquiring data automatically. And not only doing that, they're also scanning from a tripod perspective, and they're merging the two data sets together, which I've seen. It's incredible. Hopefully I get to show you guys one day. So they're merging these data sets together, and they're archiving this data set so for to reference back, for any reasons. And then we got to do the Swiss guys. the Sweden guys, sorry, they have a VZ1000 and a VZ400 as well. And let's go to the U.S. Yes, I know our coverage in the U.S. is not as large. It's the next file to talk a little bit about more purchasing power and whatnot, but the Secret Service here, they have a VZ400. They started off with a VZ400, and just last year, my guy over there, the Secret Service, realized the power of ladder, so somehow he managed to get the department to purchase a full-blown mobile system. I mean, these mobile systems, we sell them to large surveying and engineering companies, to map highways throughout the United States. But he's using it to map, anything he can that requires, driving. So he's got mobile capability. Army Corps of Engineering, they've had a VZ4000 for the longest time to do internal investigation within the MP, military police. Then we have the FBI. They have a LMSZ series that are still using it today. It's a legacy system, but they're still actively using it. And then our recent purchase from the San Diego, oh, sorry, that's not supposed to say police department. I apologize for that in advance. It's supposed to say San Diego Department of Public Works. Yeah, I feel bad for that. That's not supposed to say that. And then let's look at some case studies. So all of our customers throughout the world, when they did their research on buying these systems, they weren't biased. They weren't like, hey, well, let's buy the system because of cost. Let's buy the system because it was there and the first guy that came to us and we bought it. No, they did years of study. They did years of research. And one of the big cases that came to the conclusion of them purchasing these large quantities of systems, especially Great Britain, is that reduce road closure. Bottom line, they needed a system that worked, that was able to handle rough condition, that was ease of use, and it was fast. It had a fast working workflow that can take data acquisition to deliverable within nearly the same or next day, right? So they choose the Riegl system because it met all those criteria. Now, our system, the Riegl system, yeah, perhaps it was a little bit higher in cost, but nevertheless, they choose the Riegl system because of quick deployment, and it works, the system that works. And here are some case studies. Please contact me directly, and I can give you links to all these case studies, and they're all online too as well. And our last purchase was through the Welsh government, right? So, and they did the same study. They wouldn't just buying these systems. They all had these valid case studies that said, hey, although the system costs more, we wanted this system for X amount of reason. And it's all listed in the article there. And here's just newspapers and articles throughout the world that these case studies were done on. And they're legit and they're real. You can find them. They're all over the internet. And last but not least, if I can, I'd like to show a video. I know our time is up, but should I do that, Eugene?
Yeah, is it a long video or what's?
It's about 3 minutes, and I'll fast forward.
Okay.
And these images, I have to say, images are courtesy of 3D laser mapping as well. And some of you have already seen this video, maybe not.
I'll tell you what, Tan, while this is playing, could we just cover off on a couple of questions?
Yeah, absolutely.
Okay. There's a question here about E57 file format and if it's possible to import into RiScan Pro now.
Ananda, you're the software development. You want to take this?
Yeah, sorry, I'm getting drowned by this thing. Okay, so they want to import the file back in, or they want to colorize using the iStar data? Like, I don't get the question.
They're just asking if E57 can be imported into RiScan Pro. I don't know if that was related to. I can't tell here if it's related to the same iStar question. But is E57 allowed to be imported into RiScan Pro at the moment?
At the moment, no, we don't import E57.
Okay.
But if it's a request, I would like to hear it, because it's not something that's impossible. Of course, we can do this in the future.
Okay. If it's related to the iStar question, then I think that is the that might be the issue, because the iStar software, color cloud, whatever, will recolor E57 files, but once they're recolored, you need a way to get them back in. So maybe that's that what the question was referring to.
Okay.
Maybe.
Yeah, no, at the moment you can't import it back in, so I will make a note of that, and it sounds like it's needed, so we'll put it on the roadmap.
Okay. Any other questions from the audience? I think I don't see too many more. We did the iStar one, we did the export one. Let's see here. Somebody else. Somebody's asking, what is the field of view of the scanner?
It has approximately 100 degrees vertical, and it'll rotate 360 degrees. If you wanted to scan above, we do offer a tilt mount that you can tilt the scanner 90 degrees. So, yeah, 100 degrees. So if you put your arm straight out, if you go 60 degrees up and then 40 degrees down.
Okay. Well, I'll tell you what, we're a little bit over time, but I do want to thank both of you for a very informative webinar. Lots of good technology there, and it always helps to get a little bit of insight into what you guys are doing under the hood, because oftentimes we don't get to learn about that stuff. So again, Ananda from Austria, thank you very much. Tan from Orlando, thank you very much. This webinar is being recorded, so it will be up on our website probably in the next couple of days. We'll make it available for those of you who missed it. And thank you all for attending. If you do have any further questions or you have any other information, you can direct it to us directly at the IAFSM, so info@iafsm.org. Kathy Lochner will get those, and she can forward them on to Ananda or to Tan. Or if you caught Tan or Ananda's email or contact information at the beginning, I imagine they can send that to you directly, guys, and hopefully that's not a problem.
Yep,
yeah, of
absolutely.
course.
Thanks everybody for attending.
Yeah, thanks a lot. Thanks a lot, Eugene.
Okay, guys, all the best, and have a great week. Bye-bye.
Thanks, likewise. Ciao.
Yeah, see you in November. Bye.